All right. Today we're going to see the third law of Isaac Newton of for motion, and it's one of the more important and interesting laws, which needs quite a bit of deep understanding so that you do not confuse multiple different stuffs which are involved here. I'm going to try to specify those things so that you do not feel confused. And Newton's third law is actually a law that applies everywhere. It is applied for the macro case world. It is also applied for quantum world as well. It is one of those laws which is practically universal in all scenarios. Up so far, the scientists have found out. There hasn't been a single scenario where Newton's third law is not applicable. So it's pretty interesting. The statement of Newton's third law is actually quite simple. It simply says that every action has an equal and opposite reaction. In this case, these two words, action and reaction, they practically mean force. What this means is that if we have two different objects which are going to undergo some amount of collision, they are going to experience equal amount of force exert onto each other in opposite direction, and this will happen for the same duration of time. And there are multiple other criteria for Newton's third law. Let me give a very simple example. You kids have the concept of momentum in your syllabus, but you do not have the concept of what is it called? You do not have the where is my download folder? Documents. So this would be আমি এটা সার্টেন জিনিস দেখার জন্য সিলেবাস বের করছি, একটু দেখা দরকার। সেটা হচ্ছে তোমাদের কনজারভেশন অফ মোমেন্টাম আছে কিনা, কনজারভেশন অফ মোমেন্টামের লটা আছে কিনা, থাকতেও পারে নাও থাকতে পারে। So I just want to have a look at it. They have given the momentum, they have defined the impulse. Yeah, you have the principle of conservation of momentum for simple problems in one dimension. Okay, fine. Yeah, we can go ahead and see what go ahead and check what it is doing. Let's try a very simple scenario. Let's say we have an object of mass m1 which was initially moving in this direction of u1. In the same line of this object moving, we are considering this object to be an isolated object, which means it is not subject to any force yet. So assume this whole thing in a certain location where there is no gravitational force. So not considering on the surface of Earth, or even if you're considering the surface of Earth, try to imagine the object rolling on a frictionless surface, something like that. In the same line of movement, in the same direction of velocity, we have another object which is right in front of it. Let's say that object has a mass of m2 and it is moving with a smaller initial speed u2. Now for the initial case, let's say u1 is bigger than u2, so which essentially means pretty soon this object is going to hit this object. And once the collision actually happens, ultimately this is before collision, sometimes after we're going to have the collision. Let's say that when the collision is happening, this is our m1, this is our m2, so I'm going to write these two, m1 and m2. Let's say these two objects are going to collide onto each other. M1 is going to apply a force onto the M2 object. Let's say this is force F2, the force experienced by object F2. By Newton's third law, object M2 will also apply an equal amount of force in the opposite direction on M1. So this force is going to work in this direction. Let's say that force is F1. One thing is very important, that the existence of these two forces is going to be equal for both of them, which means if object 1 applies F2 force on object 2 for a duration of t, that F1 force will also exist for a duration of t. That's why I'm writing this variable t over here, because I cannot actually draw t over here. So I'm just writing this t over here in a rectangle to signify that time is a pretty important variable which is going to come in handy after a while. So let's say the collision happens for a small duration, and then after the collision, this object F2, this force F2 is working in the same direction as the U2, so this object is going to speed up, and this force F1 is working in the opposite direction of U1, so M1 is going to slow down. So after the collision is finished and they actually separate from each other, let's say after collision their velocities are going to be like this. So this is our M1 and this is our M2. Bigger might be good. M2 and M1 keeps on moving in the same straight line with the final velocity of V1, whereas M2 keeps moving in the same straight line with the final velocity of V2. And in this case, V1 is smaller than V2. And obviously for this whole scenario, you need to understand that the acceleration of A1 happened in the towards left, acceleration of M2, which is let's say A2, happened to the right. So this is a scenario where we are having a scenario for, this is for before collision, this is for during collision, and this is for after collision. These are the three different scenarios that we have. So Newton's third law tells us that every action has an equal and opposite reaction. Why isn't my phone getting silenced? Okay, got it. So Newton's third law tells us that F1 should be equals to minus F2. I have a reason to write this thing as minus, because these two forces as vector quantities are working in opposite direction. Then I'm gonna convert this into the second law expression, so I can as well write M1 into A1 equals to minus M2 into A2. That can be one expression from this expression, which is a perfectly okay equation. Another version to break this down, I can also write that delta P1 divided by T should be equals to delta P2 divided by T minus. Now, if you wonder where is this expression coming from, this expression is coming from this line. Where is that line? This line, this expression that we have seen in our last class on Wednesday, that force can be expressed as change of momentum divided by time, which we call it rate of change of momentum. So we are using that expression for breaking down the forces. We have P1 and P2 individually different because these two are exclusive for the two different bodies, whereas T is a common variable for both of them because the collision happens that is same for both of them. The duration of collision is equal for both of them. So if you get rid of the T on both sides, what we can get that change of momentum of object 1 is equal to change of momentum in object 2, but it happens in the opposite direction. This equation is a very important equation. Whenever any two objects will interact with each other, they will always interact with each other for the same duration of time with each other. So one of the body's momentum change will be always equal to the other body's momentum change, but that change, these two changes should happen in opposite direction, exactly opposite direction. That is very important. I'm going to get into the 5 different properties of Newton's third law. I'm going to talk to you about those as well, so we can have a look at that just after a while. But let's just go ahead and try to elaborate this equation a little. So change of objects, change of momentum 1 can be rewritten as mass of object 1 multiplied by v1 minus u1, that is the difference in velocity, final velocity minus initial velocity, minus mass of object 2 multiplied by v2 minus u2, and that can be multiplied as m1 v1 minus m1 u1 equals to m2 v2 plus m2 u2. If we do the side change, and for a convenient case, we can write m1 u1 plus m2 u2 should be equals to m1 v1 plus m2 v2. Now, this equation that we actually get all the way from Newton's third law is called the law of conservation of momentum. I'm going to break this mouthful name for you word by word. This is a law of conservation of momentum. Whenever we say anything is conserved, or the word conservation, this actually means, for the case of physics, conservation, TION, conservation. This means that certain physical quantity is going to remain unchanged. Now, if it's a velocity, if it's a vector quantity, it is going to maintain its direction and magnitude both. If it's only a scalar quantity, it's going to only be constant for the scalar quantity's magnitude. For example, pretty soon in our work energy part chapter, we're going to learn it here, another law, the law of conservation of energy. Apart from nuclear cases, energy is a conserved quantity for macro scale of the world. So we can always have one type of energy converting into another form of energy. But since energy doesn't have any direction, we don't have to bother about the direction. But if we say it's the law of conservation of momentum, this essentially means that the direction is also maintained constant. What this actually means? This actually means, if I just try to show you over here, m1 u1 basically gives you the momentum of the first object initially. m2 u2, have a look over here, we have m2 means the mass of the second object, u means the initial velocity of the second object, which means if you do the multiple of these two things, this gives you the initial momentum of object 2. So this is initial momentum of object 1, this is initial momentum of object 2. If you sum these two up, you get total initial momentum of the whole system. System in this case refers to the total considered scenario that consists of these two objects. So we are not considering anything else involved over here. And these are the only two objects which are going to exert some force onto each other. So we are considering that there is no existence of other forces. Even if there is some other force involved, their effects are negligible or they are counteracted by some other forces. So F1 and F2 are the only forces that these two bodies are subjected to. That's what we mean by the isolated system made by object M1 and M2. So if you have a look over here, M1 U1 plus M2 U2 is basically the initial momentum of the whole system before the collision. And then if we see over here, this is the final momentum of object 2. This is the this is the final momentum of object 1, M1 V1, and this is the final momentum of object 2, M2 V2. So this is the total momentum of the whole system after the collision, which is basically represented in this diagram. So we can write, if I am trying to write in words, that total momentum of involved bodies, or you can write objects before collision, and this is total momentum of involved bodies after collision. This is the law that we define to be the law of conservation of momentum. For your syllabus, you only have to learn it for one direction. One direction means you don't have to consider a case where two different objects might have different direction of velocity, which means the simple example that I've shown you over here, that the two initial velocities were aligned in the same line. So they're both moving in the same direction. And even after collision, they're also keeping on moving in the same direction. We simply have to consider up to this much simple expression for your level. It is possible that objects after collision can go in two different directions, which is very common case for coplanar collisions that we use in a lot of different sports, indoor sports. We use it in carom, we use it in pool or snooker. We can shoot a ball on a surface, and after they collide, they can have the two objects going two different directions unless you're actually playing a stop shot or a rolling forward shot. For those of you who know what these things are, you know what I'm talking about. For those who don't know, don't bother. These are not very important examples. But for your syllabus, you don't have to consider whether the objects are going to move in different directions. You simply have to consider the scenario for the same linear direction. That's why I'm not going to show you the angular breakdown of these two stuffs, or the component variation is not needed for your level. We're going to see about the two-dimensional or maybe three-dimensional collision in the AS level, depending on how much syllabus change are we going to have for the AS level syllabus. So this is basically the law. If we want to write a sentence-based description or sentence-based expression of the law of conservation of momentum, this is how we can write. There can be a lot of different ways to express this term. As long as you understand what you're writing about, you can flexibly choose your words, but just don't choose the wrong set of words. As long as you understand the concept, you should be able to articulate it properly. You should be. One of the version can be, which comes to my mind right now, is that the total momentum of colliding bodies, I'm going to use plural, total momentum of colliding bodies before a collision is equal to total momentum of the colliding bodies after the collision. That's the expression of the law of conservation of momentum. It's pretty simple. In many cases, we actually can write these kind of sentences, and you might actually see this kind of word expressions in my teaching a lot. What I just did is I just renamed this equals to sign exactly what it is equal to. I just said it right exactly. So I'm said total moment of colliding bodies before collision is equal to total momentum of colliding bodies after collision. That's basically what I said. So that's the idea. This equation come in handy for a lot of different cases, and we're going to see some mathematical expressions for these maths just whenever we're going to start solving some worksheets and pick up some problems from the chapters. So we don't have to worry about examples for the time being. There is one more thing that I'd like to talk about, is that this law, Newton's third law, it has multiple different properties which is embedded within, which we need to talk about to specify those out so that you can understand them rather better. But before I get into that, I'd like to know that do you have any question about this whole discussion, about this whole collision and the equation derivation parts and anything about that? Anyone, any questions so far?
No, sir.
Awesome. So the important thing about this Newton's third law of collision, I mean, there are 5 different properties which I always prefer to teach the students, because you kids need to understand that. One of the properties is that, as the question says it, the forces are equal. The second direction says forces are in opposite direction. এই দুইটা ইজিলি বোঝা যায় কারণ এই দুইটা অলরেডি আমাদের লয়ের স্টেটমেন্টে বলে দেওয়া আছে that the two forces are every action has an equal and opposite direction, so it's immediately says in this thing. Now one thing I need to understand, or I think one thing I need all of you to understand, whenever we say two different vectors are in opposite direction, it does not necessarily mean they're in the exact opposite direction, because this can happen. Let's say you have a car that is moving towards east at some speed, let's say 30 kilometers per hour. Maybe you have another car that is moving towards west on the map at maybe 50 kilometers per hour. If you are asked, are these two cars moving in opposite direction, your answer has to be yes. Are these two cars moving in exact opposite direction? For my drawing, that answer is a no, because the alignment of their velocities are not same. They're parallel, but they're not same. Understand this. Two vectors can be in opposite direction, but not aligned. For Newton's third law, these two vectors, force 1 and force 2, will be always work in the same line. So their alignment should be exactly same. So the third property, which is really important, same alignment. Fourth property that we use, these two forces work on different objects. Now, this is very, very important. This is the point which I'm going to take some significant amount of time and effort to explain to you with multiple examples. This is the concept that in many cases students mess up for the application of Newton's third law. And number 5, same type of force. Same type of force is pretty easily understandable. This means that if one of them is a gravitational force, the other one will also be gravitational force. If one of them is a contact force means two objects being in touch and they're pushing onto each other, the other force will be also contact force. If one of the force is electromagnetic attraction, or maybe electrostatic attraction, or magnetic attraction exclusively, the other one will be of the same type as well. If one of them is a strong nuclear force, which is a type of force, you don't have this in your syllabus, but this is the type of the fundamental 4 type of forces available in the nature. So it can be if one of the forces is a strong nuclear force, the other one has to be a strong nuclear force. Bottom line, these two forces cannot be of different genre. These two forces cannot be of different type. These two forces will always be of the same exact type. Oh, one of your classmates asked for a bit more discussion for the third point. The third point is same alignment, which means these two forces will always work exactly in the same alignment. You cannot have one force work, let's say over here, the other force working in the opposite direction, but not in the same alignment. This kind of scenarios cannot happen for Newton's third law applications. The two forces must be in perfectly or exactly opposite direction to each other. বুঝছো?
So they must be in a line.
বুঝি নাই?
They must be in a line, like opposite direction, but in the same line.
Yeah, that's basically what alignment means. Yes, they have to work in the exact same line. Yes. Achha, number 4.
Could you repeat the explanation of number 2?
Number 3.
2.
Yeah, this means that the two forces must have the same line of action. Same line of action means, in this case, if you have a look over here, the way I've drawn these two forces, that they have the same working alignment. I mean, it's not possible that one force works in one direction, the other force might work in the opposite direction, but not in the same alignment. That's not going to happen. I mean, you cannot have a scenario, let's say, where two objects collide with each other, maybe like this, where for one object the force works this way, for the other object the force works this way. I mean, if you consider, if these two lines are parallel, let's say if these two forces are parallel, if I'm just saying that, let's say these two forces are parallel. If these two forces are parallel, you have to say that these two forces are working in opposite direction. But are these two forces working in the same alignment, or are these two forces working in the same line of action? Do they belong to the same straight line? That answer is a no. If that is the case for any scenario, they are not Newton's third law pair forces. Third law pair forces will always work exactly in opposite direction, belonging to the same straight line. বুঝে গেছে?
Yes, sir. Thank you.
No problem. The fourth point is these two forces work on different objects. Let me elaborate this point by going through some examples and a bit more discussion for relevant. One of the important bits to understand Newton's third law in practical scenarios, that you need to understand that the effect of Newton's third law does exist in every single case. It is inevitable and irrefutable. But whether the effect of that force will be perceivable, whether we can understand or see or sense the effect of that force, that is somewhat uncertain. I mean, can we perceive the effect of the force? I mean, that is somewhat uncertain. Let me give you a bit of an example. For the sake of what do I mean by imperceivable, or something that cannot be understood. On Earth, we strongly experience the gravitational pull of Earth. I mean, you try to take a jump upwards, you're pulled back. You try to shoot something upwards, it's pulled down. If you want to go into space using a rocket or something, you have to use extreme amount of force. to go there. I mean, you are really pulled down towards the center of Earth. That is inevitable. But you have to understand that Sun is a significantly more massive object than the Earth. Sun is so massive that it is actually pulling the Earth towards its own center, and that's why the Earth orbits around the Sun. So if Sun is pulling the whole Earth, we are belonging on that. We also have mass. So essentially, Sun is also pulling us as well. That has to happen because we have mass. Sun has mass. Sun is pulling the Earth. We are on the Earth, but we do have mass. So Sun is also pulling us. But do we ever, by any means, by any physical, visible, understandable way, actually feel the gravitational pull of Sun? Do we? In any experience of our life? We don't. But we don't, that doesn't mean that the Sun doesn't pull us. It simply means that the pull of the Sun is significantly smaller compared to the magnitude of pull of the Earth. The pull of the Sun is so small for between the gravitational attraction that exists between, let's say, my body and the Sun is so small that it almost becomes negligible for the physical senses that we have. But if you are asked that does the Sun pull Faisal sir or not, you have to say yes. You cannot say no. But can we sense that effect? Or maybe can we measure it? That answer for all practical purposes can be no. So that is the important bit that you have to understand. Let me give you some more examples for Newton's third law application. One of the first examples that I always give is that whenever a footballer, let's say a goalkeeper, is taking a goal kick, or let's say a normal footballer is taking a free kick, for example, they're taking a free kick. So they place the ball on the football field, ran up by a short distance, and then kicked the ball, and the ball moved away. This is a very simple and very beautiful example of Newton's third law. How does the ball actually gets accelerated in the atmosphere? The person kicks the ball, so the footballer's feet gets into contact with the ball, pushes on the ball for as long as the person's feet and the ball is in contact, and by hello.
Yes, sir, we can hear you.
আমি একটু সময়ের জন্য ডিসকানেক্ট হয়ে গেছিলাম। তোমরা কি শুনো নাই?
Sir,
মানে
the food.
I picked up the example for the footballer. Did you hear that?
Sir, the examples শুনেছিলাম।
হ্যাঁ, ফুটবলার এক্সাম্পল হচ্ছে, মানে সানের এক্সাম্পল শেষ করে ফুটবলার এক্সাম্পল আসলাম। এটা শুনছো তো?
জি।
আচ্ছা, ঠিক আছে, বলতেছি। So for the duration that the footballer actually executes the kick, so from the instant that the footballer actually is in contact with the ball and to the point of time when the ball actually leaves from the contact of the footballer's leg, within this time the footballer exerts some force. Now in this entire process, the footballer exerts some significant force on the ball, which you can see because the ball whooshes away, it actually flies away. By Newton's third law, the football also exerts a significant force on the footballer as well. Now that force might be imperceivable for our regular experience, but I can make it understandable for you. Hear me out on this imaginary scenario. Let's say there is a ball and there is a footballer. Any footballer is about to take a short run up and about to take the kick. Let's say typically what happens when the footballer takes the kick, they pretty much stands there and the ball goes away. Now here's an idea. Let's say the footballer is about to take a run up and they're about to take the kick. So they have undergone the entire motion of the kick, but the instant their feet is about to touch the football, let's say suddenly the football vanishes. The football is not existing there anymore. So they saw the football, they were mentally prepared, they took the physical run up and are about to take the shot, but let's say at the instant of the contact, the football suddenly vanishes. What is going to happen? What's going to happen to the footballer? Are they gonna be able to stop, or they're gonna practically take a stump and might fall on the ground? What's gonna happen?
On the fall.
The most likely scenario is that they're gonna fall. I mean, why do they fall? I mean, why is that? Because the motion, physical motion of football, of taking the kick, is that we try to exert a huge amount of force on the football. So we actually make our body unbalanced, and that's how we can exert exert the biggest amount of force on the football. Whenever the kick happens, the football exerts an equal amount of backward force onto our body. That basically decelerates the player's body, and that's why the player actually is no longer falling down further. The player pretty much stops at the position where the football, where the kick was taken. But before the kick happened, the footballer actually did take a short run up, so they had some initial velocity. So the football did apply a force backward onto them. That's what decelerated the footballer, and that's why they came to a rest position after the kick was executed. So in this case, what you have to understand, that the football is given a positive acceleration from rest, it started to move forward, but the footballer was given a negative acceleration in the backward direction of their velocity, which practically stopped the footballer. The force exists, but it might be difficult to perceive. Second example. Do you kids know what a high jump is? I'm not talking about long jump. I'm not talking about pole vault. I'm talking about high jump. Okay, let me just show you the difference. This is pole vault, that you have a person who takes a run up with a stretchy rod, and then they catapult them over a certain point. Long jump is basically a horizontal type of jump, where a person tries to cover as much distance on the ground as possible. So this is the sort of the ground figure for a long jump. High jump is basically where a person tries to cover as much as possible, as much as height possible, without the help of any instrument. So high jump is basically like this: a person takes a small run up, and then they just shoot themselves out of the ground. So we have a GIF. Wouldn't this thing play on their own? No. No. I hope nothing weird shows up, because Jiffy can be a pretty dark place. Okay, here we have a high jump scenario. So I want all of you to see this image, high jump sport GF. Okay, have a look at this, at what is happening to this high jump motion. Why is not playing? Okay, playing. So the person is taking a run up, then they're taking a bit of a curve, and then they're making the jump above a certain horizontal bar. So that's basically high jump. Now, the point that I'm trying to make, is there a way to pause this? Maybe not. So I'm gonna just get back to over here so that you can hear me and not concentrate on the jump. How does a person actually executes a high jump, or how does any regular person executes a jump? Let's say, even if I'm trying to make a jump above the ground, just for whatever reason, so I'm just trying to show how much of a static jump that can I make. What's going to happen? Whenever a person is trying to take a jump, they have to bend their knees, and they're going to lower themselves, and then they're going to exert, they're going to shoot their feet downwards at a very high speed with the best of the capability of the muscles they have in their legs. Within this process, they're going to exert a significant force on the ground. In that process, now this is the action force. The person is exerting a downward force onto the ground. By Newton's third law, the ground pushes an equal and opposite amount of force onto the person's body. So try to understand this, right? Visualize this thing. Person pushing the ground, this is the action force. This force is provided from the person and working upon the ground. In other words, the earth. Person is pushing on the earth. But in a third law, earth will also push the person by the exact equal amount of force. As a result, the person is going to be able to take a jump off the ground. And why the jump happens? I mean, what does the person have to achieve to make that jump possible? We all have a weight. For the jump to happen, we have to have some duration of time for which our body is not in contact with the ground. That's basically what we call a jump, that you actually have gone above the ground level without touching it. So to execute that, you have to push the ground by a force that is significantly higher than your weight, so that the ground in return gives you an equal amount of force, which is also higher than the weight force. Now, Earth is pulling you down because of gravitational pull, which Earth is not never going to let go. And you are now pushing on the ground an action force, which is a contact force. Earth is, because of the effect of this contact force push downwards, the Earth will also exert an equal amount of upward force onto the person's body. Using this reaction force that is available from the Earth, the person is going to overcome the weight and is going to be able to make that jump. Now, point that I'm trying to get at, I'm going to come into the discussion of weight and the jump forces after a while. That's going to be a part of a different direction, different discussion right after this. But what I want you to understand, in this case, for this example, the action force was the push of the person downwards towards the ground, and the reaction force was the Earth's push onto the person in the upward direction. So both of them exerted equal amount of force onto each other. We saw the person took the jump. So the force that the Earth exerted on the person is seen to have a visible effect. So if you consider the scenario, if you consider the equation F equals to ma, the Earth pushed some force onto the person's body. Person have some mass, so we saw some actual acceleration because we saw the person taking a jump. To have that force available, the person also pushed the ground downwards. Do we ever perceive any measurable experience that the Earth has accelerated even by a little bit because of the high jump of a person or because of the jump of a regular person? Does that happen?
No.
Do you ever feel that the Earth just shook a little bit for a fraction of a second because someone took a jump? We don't ever perceive that. Why? Because this same force is also equal to the mass of Earth multiplied by the acceleration of Earth. This force might be very large. This force maybe, let's say, maybe 100 Newton, maybe 150 Newton. 150 Newton working on the person of a, let's say, of a 50 kg mass can produce significant acceleration. But actually, let's say 1000 Newton. 1000 Newton working on a person of 50 kg mass can give a significant acceleration of, let's say, 20 meters per second, which is significantly bigger than the gravitational acceleration of 10 meters per second squared. The person can make a jump. Well and good. But this same force, 1000 Newton, applying on the huge mass of the Earth, which is about 5.9 into 10 to the power 24 kg. I just know this value, that's why I'm quoting this. You don't have to remember or memorize this value. This is the approximate mass of the Earth. This acceleration would not physically exist. But if you want to calculate that mathematically, can you calculate a number? The answer is definitely yes. You can definitely calculate a number. Does that calculated number actually mean anything for physical world? No. So if you are asked, when the person pushes on the ground and the person is pushed upwards, the force, the Earth pushes force onto the person's body because the person is able to make the jump. And by Newton's third law, because Newton's third law works, to avail that force, to avail that upward force, from the ground, the person had to push the ground by an equal amount of force as well. By Newton's third law, both of these forces exist, but the effect of this first force, action force, is not understandable. It's not perceivable. That doesn't mean the force doesn't exist. It does exist, because without that push, the person would not get the reaction force. I mean, if I'm standing on the ground, just standing, I'm not going to be randomly pushed upwards unless some eruption happens under my feet, which I hope never happens. At least not while I'm alive, but you get my point. The effect of action and reaction forces might be visible, might not be visible. The third example is very simple. If there is a scenario where two persons are on a low friction surface, which can be in a lot of cases, let's say you can have two people on roller skates. Here are two people on roller skates, and they try to push each other, or let's say even one try to push the other one. We will see that both of them would move away by some distance. They might not be on roller skates. They might also be on ice skates, which is going to give us a much better example. Or even better, they might be on two different boats with equal masses maybe, and they're gonna, if they try to push each other away, If one person even exert a force onto the other one, we're going to see both of them move away from each other. The reason we're going to see both of them move away each other is because Newton's third law work. This is also a very good example that how multiple things actually, to be honest, whenever we consider the scenario of any type of achieved movement means that we actually put some effort to achieve the movement of something. Whenever we make any object move, be it ourselves, be it anything, or any other object, vehicle, locomotive, whatever, Newton's third law works in every single scenario. I mean, if you try to understand that, how does an object actually move? The only way any object can move is that they have to apply Newton's third law. If you have an object with an initial velocity u and you reach to a final velocity v, you have to have some acceleration in between. Acceleration must result in from some force. How do you get that force? To get a force, you have to apply some force onto something, and there is absolutely no other version of it. If you want to be pushed forward, you have to push something backward. It has to be something. Now, it can be this sentence that if we want to get a force in the forward direction, we have to push something in the backward direction. This sentence can be elaborated by a huge number of examples. Like, there is practically no end of how many different examples I can put. So I'm going to try to bring up the most simple ones, which in your syllabus is discussed with importance. So I'm going to pull up one example that is, how do you walk? How does this basic human being, or maybe Chatushpat Prani as well, four-legged animals as well, how does a person walk? Let's say this is a ground. These are the feet of a walking person. This is the front feet for the time being. Let's say this is the left feet, and let's say this is the right feet for the time being. So the person is taking a continuous walk, and at the time being, this is the feet that is on the ground. Okay, so the person goes up like that. I'm only drawing the feet, so the person does exist over here, so I'm not drawing the whole person. I'm drawing a break sign representing the figure continues. How do we walk? The key process by which we walk is that, I'm not talking about running, I'm talking about walking, is that whenever the feet that is in front of our body, for example, the forward feet, we use that feet to support our weight. So whenever we are walking, we pretty much apply significant portion, not all of it, significant portion of our weight through our feet onto the ground, and the ground gives us exactly equal amount of force that we exert through our feet, which basically supports our weight. Through our hind leg, the leg that is behind, we push the surface backwards, and because Newton's third law work, and provided there is enough friction between the person's leg and the surface that we have over here, provided the surface is rough enough, it's not oily, or it's not slippery, or maybe it's not loose sand, or it's not wet, provided there is enough friction, the surface also exerts an equal amount of force onto the person's foot on the forward direction. This force we use to simply stay on the ground. This basically make us exist on the ground. This is the force that we exert on the surface, and this is the force that is available to us so that we can make our body move forward. This is the force for which we move forward. It's very important, you have to understand this thing. We apply a force behind our body, in the backwards through our feet. We actually push the ground backwards, and for that reaction, the ground pushes us forward. If you want to understand this thing in a bit more easier example, I can give you one more example for this. Acha, ekhane arta jiনিস আমি বলে নাই, সেটা হচ্ছে, this is one of the examples where friction is very useful. Yeah, we're gonna learn about friction after a while, and it's gonna show up. Many of us might think that friction is very bad because it causes energy loss and it heats up objects and everything and whatnot. This is true, but friction is one of the most fundamentally required forces of our whole experience. If friction did not exist, then multiple objects would not stuck with multiple objects. I mean, if friction did not exist, our entire skeletal system should not work. Muscles should not stick with bones. Bones should not stick with bones. I mean, friction is one of the fundamental required force for us to even experience the world that it is as is. Friction is very useful. If friction does not exist, let's say if you put a person on an oily surface, a regular person with regular clothing with no extra equipment, you just put them on a huge patch of oil, they're going to have a really hard time to come out of that thing, because every single time they're going to try to push the ground, they're not going to get enough friction force. So what's going to happen, their feet, hands, they're going to continuously slip, and they are not going to be able to get the reaction force. So all the force that they're going to try to push on the ground is not going to be pushed on the ground, rather it's going to remain on their body, and their hands and feet are going to shoot themselves outwards every single time because of the slipping effect. So we can only move forward because friction is available. This is going to be also available for turning as well. I'm going to talk about that after a while as well. If I pick up the second example that I usually go for, is that if you think of it, let's say here is a actually, before I go into the second example, did you all understand the first example? Do you have any question from here? Does this example make sense? I have a question in the chat. Okay, no. One of your friends responded yes. Rest of you, the four of you, rest four of you. Did you understand this example about the action and the reaction forces? বুঝা গেছে কিনা?
Yes, sir.
Yes, sir.
আচ্ছা. The second common example that I usually go for is that, consider a scenario. Let's say this is water body, and ঘাট কে ইংলিশে কি বলে? ব্যাংক না, ব্যাংক তো হচ্ছে তীর. Human made structure that we make to make the boarding easier. What do you call that structure? Jetty না. বলুন কেউ একজন মানে এই বাংলা ওয়ার্ডটার ট্রান্সলেশন কি? ঘাট, নদীর ঘাট, পুকুরের ঘাট, ভুলে গেছে.
The translation is ghat.
না, translation is মোহনা.
No, sir, the ghat. English translation of ghat.
Should I look it up? ইংলিশে কি বলে ভুলে গেছি আমি. ঘাট translation. Okay, flip.
Is it port?
It can be said port, but a boat flight steps and steers on the Indian River bank. The process to the water especially for bathing. Okay, ghats apparently is accepted as the same word in English as well. Ghat is accepted in the English word as ghat. So yeah. Gat. That pronunciation is so weird. Anyway, we'll move on. So মনে করো এটা হচ্ছে আমাদের একটা পুকুরের ঘাট বা নদীর ঘাট, ঠিক আছে? আচ্ছা, let's say it's a পুকুর, let's say consider it's a pond. Let's say here we have a boat, and within the boat there is a person. For the time being, the person does not have any instrument, বৈঠা লগি বৈঠা এগুলা কিছু নাই. Now let's say if the person wants to move away from the bank, if the person wants to move in this direction, what is the most likely thing this person is going to do other than making him wet? The most common thing that a person usually does is that they're going to hold onto this thing. They're going to hold on to this, and they're going to try to push it away. So that's what we do. They're going to try to push this border, maybe a pole, maybe a wooden structure, whatever that is. They're going to try to push it away. As they're going to push it away, because this thing is very well built on the sand or the mud or the soil that we have over here, this thing is not going to move away. Rather, the person is going to get an equal and opposite amount of reaction force in this direction, and this person can actually move a bit forward. This is exactly how a Newton's third law comes into action. This is basically what is happening in this example as well. Person is trying to push the ground backwards, ground is pushing the person forward. The third example that we go for is for the case of a moving vehicle which has some wheel. Might be wheel with rubber tire for basic cars or automobiles, might as well be an iron wheel for the case of trains, but I'm not talking about maglev trains, so that's a different technology. So vehicles which move with wheels always move like this. Let's say this is the ground, and let's say this is the wheel of a certain car. Let's say this is the front of the car, this is a front wheel drive car. So let's say this is the car's front. Here we have the headlights and whatnot. So let's say this is the wheel, front wheel, which is being forced by the engine. The engine is connected to this wheel. So when the engine is going to run, the person is going to put the accelerator down and let go of the clutch. The car is going to start moving forward. So this is what we call the driving wheel. So let's say within this driving wheel, whenever the engine starts to run, the wheel starts to rotate. So to move the car forward, the wheel has to rotate in a clockwise direction. For my view, so it has to go like this. So what happens when the wheel starts to rotate clockwise? A portion of the car's weight is applied to the wheel on the ground. So let's say I'm going to label that applied weight over here. So let's say this is a fraction of the weight. Just for the sake of discussion, let's say a car has 4 wheels. So about 1/4 of the weight is applied to one of the wheels. So the wheel is going to apply this force on the ground, and by Newton's third law, the ground is going to give the wheel upwards the exact equal amount of force. These two forces will balance each other. Actually, I shouldn't say these two forces will balance. I will say that this is the force using which the car actually stays on the ground. But whenever the wheel is turned, or whenever the engine is turned on and the accelerator is pressed down, the wheel starts to run. Because there exists enough friction between the car wheel and the ground, as the wheel starts to rotate, it actually starts to push the ground backwards. By Newton's third law, the ground then pushes the wheel in the forward direction. This is the force on the ground from the wheel. This is the force on the wheel from the ground. These two are Newton's third law pair. Because this force exists, this force comes into action, and that's why the car can move forward. Now, if your engine runs with high amount of force, you can get a bigger amount of torque, you can move really fast, you can accelerate faster, and so on and so forth. So that's basically the idea of movement. Now, this is not going to be available if the ground is slippery. For example, if you try to run a regular car, on a snowy road without much grip, you're going to see that the snow is being flipped backwards. Or maybe if you try to run a regular normal car, not a Jeep, in a desert, you're going to see that sand is being flicked backwards, but the car is not moving forward. The idea is very simple. For those scenarios, those cars are not having those cars wheels are not having enough friction, enough grip onto the underlying surface, and as a result, all of the movement is causing the physical movement of this pavement or of these rubbles and the sands, everything. And because this applied force is used to move these objects in this direction, the wheel is not getting enough force in the forward direction. It is the applied force is actually used to move them forward because the friction is not there. Do you understand?
Yes, sir.
ঠিক আছে, সো এরকম আরো অনেক এক্সাম্পল দেওয়া যাবে। যেমন আরেকটা এক্সাম্পল হচ্ছে যে মনে করো হচ্ছে whenever any waterboard vehicle actually moves forward, আমি একটা এক্সাম্পল দেখাই। মনে করো এটা হচ্ছে আমাদের ওয়াটার লেভেল, ঠিক আছে? এটা মনে করো হচ্ছে একটা স্পিডবোর্ড, রেগুলার স্পিডবোর্ড। মনে করো এটা একটা আউটবোর্ড মোটর আছে, এই হচ্ছে আউটবোর্ড মোটর। এখানে হচ্ছে আমাদের আউটবোর্ড মোটরের ভেহিকল এন্ড এভরিথিং। এখানে হচ্ছে আমাদের প্রপেলারস, ঠিক আছে? এখানে হচ্ছে আউটবোর্ড মোটরের ইঞ্জিন। Here we have the people doing memes and everything, so taking selfies and everything, whatever, ঠিক আছে? So এখন let's say this board, this to make this speedboat move forward, they're gonna start this up and eventually they're gonna run this. So this propeller is gonna rotate, and in the process of rotation, what is it gonna do? These propellers have angles in them. So let me show you a view of a propeller so that it might make better sense to you. So have a look. Yeah, this is one of the images of a propeller. This is how a propeller looks. So you can see those angles, right? This is the body of the ship, and this is what we call the hull. This is used. No, this is not hull. This is called rudder. This is the hull. This is the body of the ship. This is called the rudder, and the rudder is basically what controls the direction of the vehicle. So what is happening here? This is the main propeller, which is gonna cause the boat to run. And you can see this propeller is really large. This belongs to a very large ship. Obviously, he is a standard person, might as well be a European person, so might be as well be taller than the average people in the on Bangladesh. But irrespective, this is a very large propeller. You can see those angles. The purpose of this angle is that whenever this propeller is going to rotate clockwise, so if the propeller is going that way, it's going to hit the water molecules at some angle. So whenever the water molecules are going to hit over here, because of this angle, they're going to be pushed outwards. They're going to be pushed outwards. So they're going to be pushed in this direction. Now that's the idea. The propellers have angle so that as they will hit the water molecules, when the water molecules will leave from the propeller, they're going to move in the exact opposite direction of the velocity. So after the collision, the water molecules are going to move in this way, and because the water molecules will move this way, they're going to apply an equal amount of momentum change on the propeller. So that's essentially what we saw in our equation right over here. Delta P1 equals to minus delta P2. Where is that? There it is. Delta P1 equals to minus delta P2. So if you consider, let's say 1 gram of water, or maybe 1 drop of water, maybe 1 molecule of water, for example, if you make a small amount of momentum change of a water molecule in the in this direction, that propeller body will experience the same amount of momentum change in the forward direction. So if we rotate this propeller fast enough, we're going to be colliding with a huge number of water mass, and that huge amount of water mass interaction is going to give us a huge amount of momentum change for the whole water body, because water will be pushed backwards, the propeller is going to be pushed forward, and because the propeller is attached with the boat's body, that's what causes the entire body of boat or ship or whatever tanker, it has to move forward. So the boat simply doesn't move forward by some magical means. It's very simple. It has to push the water back to make itself move forward. It's a very simple application of Newton's third law. Because of the action force in the backward direction, we gain the forward force we get the reaction force in the forward direction. That's how the whole thing works. And as for rocket propulsion, also works in the exact same way. Rocket propulsion also works in the exact same way. Just to show you a figure. I don't want to draw a whole rocket. Do we have some? No, so transparent. Yeah, transparent rocket. Okay. Oh no, I didn't mean this. Propulsion. Yes. Got it. Beautiful. So yeah, this is a very nice image. So it's a large one. Might as well take it down there. Open image in YouTube, not the whole thing. So copy it. I don't have to copy it. You can see it already. I think you can see it, right?
Yes, sir.
Yes, sir.
Can you read this heading? What is this word? What is this word?
Payload.
Payload. Beautiful. What is this watermark? Can you read the watermark? Maybe not.
Yes, sir. No.
Okay, there's a watermark over here. Anyway, payload put the. So what is happening over here? This is what we call the first stage, and this is the second stage. This is what actually gives the huge boost to the rocket. And initially, both of these two things are joined together. This thing actually can return to Earth, which Elon Musk is doing for over a couple of years back. And that's why we have the landing legs and everything. But earlier designs didn't have a recovery mechanism, which was a bad idea. What is essentially happening for a rocket engine? We have two type of liquid gases over here, which are highly flammable. For example, we can use hydrogen, we can use methane, oxygen. We usually always have one of them to be oxygen. The other, so liquid oxidizer is basically liquid oxygen. And here we have the liquid fuel. Some engine can use hydrogen, some engine can use solid fuel, some engine can use methane. So, and they are fed into a combustion chamber over here, and this is ignited by sparks when the rocket is at the bottom level, and then these pumps actually start to deliver this thing at a certain rate. So what happens whenever these two liquid, which are actually cryogenic chambers, whenever they burn, they produce a huge amount of heating, like super amount of heating, and they expand really hard. And that amount of mass, here's the deal, it's not about volume. Try to understand, it's not about volume. That amount of mass is pushed downwards with an extremely high speed. Get this part. So here is what is, this is the equation once again, that's what drives a rocket. So if you have, let's say, the mass of the rocket multiplied the velocity of the rocket that you want to get, that should be equal to the opposite negative direction mass of the exhaust gas multiplied by the velocity of the exhaust gas. So the amount of gas that the rocket actually gives out is not that high, because you can only, you're not having an explosion, you're having a controlled burn within your engine using multiple different engines. So the mass of the exhaust gas is not that large compared to the speed of the rocket, compared to the mass of the rocket. But the speed of the gas, which is coming out of the rocket's body, is usually really, really large. So these two things product ultimately give rise to a certain value of this thing. That's what causes the rocket to slowly start to go up. And the farther the rocket goes up, the weaker the Earth's gravitational pull becomes. So using the same rate of energy burn, the rocket can actually go faster, faster, and faster and faster. That's what we can see for any of the rocket propulsion video, that as the rocket goes further away from the Earth, it usually always speeds up. It usually always speeds up. The reason it always speeds up is because it is burning fuel pretty much at the same rate, but the Earth's gravitational field is pulling it with less force. So you have more available force. You have more available force to accelerate yourself. So that's how the rocket propulsion works in pretty much all cases. Example গুলো বুঝা যাচ্ছে কিনা up so far?
Yes, sir. I had a question.
Please.
In sir, the water body example, like sir, where we push a pole, for example, sir, when we push the pole, like sir, we are only being affected by the force of the pole. But why is it that the entire boat is moving?
Oh, the entire boat moves because our feet is over here. Let's say our feet is contacting with the boat over here. So we are trying to move the whole boat as well. I mean, if it so happened that, let's say, I mean, if this person, the entire boat will move with the person's body. Did I only say the person is going to move?
No, sir. You said that the entire boat is going to move, but
yeah, if the person was standing on a boat which is dry and the person's feet are attached with the boat and they produce enough friction, definitely the person and the boat are going to move forward. But if it so happens, which is highly unlikely, that the person is standing on some roller skates on the boat surface, the boat is stuck with the thing and he is pushing onto this thing, then the person could actually move on the boat like that. That's a different scenario. But obviously the amount of, if the person's push is accelerating their own body, the amount of acceleration that you're going to get for the person, and if the person's push is accelerating the whole thing, let's say the person and the boat as well, so the amount of acceleration you're going to get for the person plus boat, this acceleration is going to be much too smaller compared to this acceleration, because the same force accelerated the person exclusively is going to give us a bigger acceleration because mass is less, and same force accelerating the combined mass of the person and the boat, this is going to be a much bigger mass, so your acceleration value would be smaller. Does that answer your question?
yes, sir. Thank you.
Sure, no problem. Any questions so far, Kolaman? Acha, I'm going to take a small break. Acha, I'm going to pause the recording here. That these two forces that we're talking about for Newton's third law, in many cases we refer to as Newton's third law pair, that these two forces will always work on two different bodies. They are not going to work on the same body. If they are working on the same body, they are not Newton's third law pair. One of the most common example to confuse or to check the understanding the students is this. Let me give you an example. So let's say 100%, yes. This is the Earth's surface. On this Earth's surface is a box. The box applies W force onto the Earth and the earth pushes the box upward by an exactly equal amount of force as reaction, which basically causes the resultant force on the box to be zero because these two forces cancel each other out. So the box stays in stationary state. It's not moving. The question is, will these two forces be Newton's third law pair?
No, sir.
I'll say the question again. Try to understand and listen to every part. The box has a weight which it exerts on the ground, and the ground exerts R force onto the box. These two forces essentially cancel out each other, so the resultant force is zero. So these two forces are equal to each other in magnitude. They're working in perfectly opposite direction. They are in the same alignment as well. So can we call these two forces Newton's third law pair?
No.
Okay, if you say no, why? Why?
Sir, because the resultant force is because we are pushing the earth, which is causing the R force.
Mhm.
So those are actually the pairs, not the R and W.
Yeah, we are pushing the earth with the W force. So the force is W. What's wrong there? We are pushing the
Sir,
earth with W force.
it's equal, but it's not exactly the same weight, which is the earth is not, the earth is pulling us with W, but the force we're applying is equal to W, but it's not the same thing.
Beautiful explanation. Try to understand what I'm saying. There are multiple different ways to judge this question. Let me go it by part. Have a look. Whenever I say the resultant force is zero, you can only consider the scenario of a resultant force for multiple forces working on a single body. Think about it. If you have one object that is subjected to a lot of different forces, let's say you have a lot of forces, you can find out a resultant force when multiple different forces work on a single object. That's the only reason you can do the resultant, because many of the forces are applying on the same object, being applied on the same object. So in this case, I'm saying that reaction force and weight are canceling each other out, and both of them are working on the same object box. That's why I could say resultant force is zero. So I cannot say these two forces to be of Newton's third law pair because they are working on the same object. Now, if you wonder what would be the Newton's third law pair then? Well, here's the deal. Have a look at the rule number 5. What is the rule number, property number 5? Have a look. They should be what? Same
Type of forces.
type of force. Now, try to understand, why does this box have the weight? What causes the weight?
Yes.
What causes the weight? Yeah, mass is obviously, and what else? G. The object has weight because earth pulls it. Why does that pull it? Because of the incident called gravitation, because of gravitational pull. So which means weight by virtue is a gravitational force. So this basically brings us to the idea. Let's say this is the whole earth, figure not drawn to scale. The mass of the earth is, let's say, capital M. The mass of the earth is, let's say, mass of the box is, let's say, small m. What Newton's third law tells us, if, let me use green for this part of the discussion, if the box is pulled by earth downward by a force of W, which is equals to, let's say, mg, by Newton's third law, the box also pulls the earth upwards by an equal amount of force of mg. These two forces would be Newton's third law pair. The box is pulled by earth, the box also pulls earth. Or I can say in direct form, not mixing up active or passive voices, is that the earth pulls the box because of gravitational force. The box pulls the earth because of gravitational force. These two gravitational forces, which happens from the same incident, they are the same type of force, gravitational force. These two are Newton's third law pair. My arrows are not very perfect. They should be perfectly in the same alignment and should be working in perfect straight line. So these two are third law pair coming up from the same physical phenomenon, gravitation. Now you might think about that. What would be the third law pair for the reaction R? R in this case was named to be the reaction force. The box, because the earth pulls the object downwards, the box applies an action force, which is a contact force, onto the surface. This surface, try to understand. When I gave you the question, I told you that the weight in this case is the weight of the box itself. I said that the weight is the force of the object itself. This weight was described in my initial question to be a force that was exerting on the object. But if you want to consider the pair force, pseudo pair force for this reaction force, you need to just consider it in a different scenario. The earth is pulling the object downwards by W force. Good. What is the box doing with the W force? What is the object or box doing with the W force? The box is pushing on the earth's surface by the W force. Now try to follow the statement. The box is pushing the earth. The box is pushing the earth with that W force, which means for this scenario that I'm using right now, the box is pushing the ground with the W force. And as a reaction, the surface of the earth is pushing the box upwards by R force. You have to understand, in this case, W was the force that was pushed on the ground, and R is the force that was given off the ground, that was provided from the ground on the object upwards. So we are naming W as two different things in our description. For the gravitation case, for the example, for the consideration of gravitation, W is defined by a force which is working on the object. The gravitational pull of earth on the object was defined as W, and the gravitational pull of the box on the earth was the other part of the third law pair. This was one way of discussing. For the second scenario, where we are considering the contact forces, I'm defining W is the force by which the box pushes the earth. So this is the force for this discussion is working on the ground, or I can say working on the earth. So W, this one force W, is now used for two different way of explaining. Two different way of explaining. Do you get my point? Maybe you don't.
Yes, sir.
I'll give you another example, which is not relevant to what is this this force scenario, but just a regular example. Let's say you have some money. Money is a generic term. If I ask you, do you have money? If you say yes, I'd say I'd understand that you have the capability to spend something. But then again, once again, in Bangladesh, if I ask you, do you have taka? If you say yes, it would mean the same thing. Because for our currency, we name money to be taka. So for our geographical region, taka is money, money is taka. But money could equally mean other stuffs on the other places as well. If you invest that money into something else, let's say you have some money, you have some taka, you invest that thing into a business, you buy some product that you plan to sell at a higher price, which is the very basic idea of any business. So that would be called investment. But an investment is basically converting that money into some feasible other product, except for one type of business, which is called banking. In banking, money is the product. They make money out of money. That's how the banking thing works. So their investment is money, their product is also money, their output is also money. So they handle the money as product. My point being that depending upon how you look at a certain scenario, you can have the same thing appearing to be different form. And that judgment in this case of force understanding is what makes all the difference. whenever you are trying to define two different forces to be Newton's third law pair, what is really important, apart from the fact they have to be equal and they have to be in the same element, they have to be in the opposite direction, what really is important that you have to judge that are these two forces that you're talking about working on two different objects? Yes or no? If yes, good. Then you try to judge that are these two forces that we are trying to consider of the same type, or in other words, I can say, are they coming up from the same physical phenomenon? Like, are they both contact forces? Are they both friction forces? Are they both gravitational forces? Are they both electrostatic attraction or repulsion forces? You have to ask yourself that question. If you can fulfill all of these things, then you can say these two forces are Newton's third law pair. Otherwise, no. The most common example is this, that one object experiencing weight, having an exactly equal amount of opposite direction force R, both of them are working on the same object. Can we name them these two things as Newton's third law pair? The answer is no, because they're both working on the same object. Or in other words, you can say they are not created, or they are not coming into existence for the same physical phenomenon. Or you could also say they are not the same type of force, so they cannot be Newton's third law pair. You could say any of this information, or maybe all of this information, depending upon how many marks do you have for that question. Did it make sense?
Yes, sir.
Everyone else, please এই জিনিসটা ভালো করে খেয়াল করো। না বুঝলে আমাকে জিজ্ঞেস করো, I'll explain again, I'll help you to understand better, but this is the part that where you really make a clean distinction between, yes, I have understood this thing, or I haven't understood this thing. If you have confusion, you ask me, I'll help you. Anyone? আচ্ছা, এরপরে আমাদের আছে হচ্ছে প্যারাশুটিস্টের গ্রাফ। আমরা প্যারাশুটিস্টের গ্রাফটা গতকালকে লিখছিলাম, তারপর ওইখান থেকে আমরা আবার নিউটনস লতে চলে গেছি। প্যারাশুটিস্টের গ্রাফ কোথায় ছিল? VT graph of a parachutist. Okay, we're gonna pick this up right now. So we're gonna discuss about this thing, and this might as well be the last part of our today's class. This is a very interesting graph, and I'm gonna try to go in detail for this one. Acha, before I jump into this one, I would like to ask one thing. তোমরা কি স্কুলে ক্লাস 8 এ ওয়ার্ক এনার্জি পাওয়ার চ্যাপ্টারটা পড়ছো? ওয়ার্ক এনার্জি পাওয়ার এই চ্যাপ্টারটা কি পড়ছো? মানে ওয়ার্ক ইকুয়ালস টু ফোর্স ইনটু ডিসটেন্স, পাওয়ার ইকুয়ালস টু এনার্জি ওভার টাইম। ইয়েস অর নো?
Yes.
আমি পড়ি ভাই।
আচ্ছা, ঠিক আছে। আমি যেহেতু অ্যাটলিস্ট একজনও বলছো যে তুমি পড়ো নাই, সো আমি কয়েকটা বেসিক এনার্জি ডেফিনেশন একটু আলাপ করব। কারণ আমি ইউজুয়ালি ভিটি গ্রাফ পড়ানোর সময় আমি ফোর্স নিয়ে কথা বলি, ভেলোসিটি চেঞ্জ নিয়ে কথা বলি, শুরু থেকে বলি ভেলোসিটি চেঞ্জ নিয়ে কথা বলি, অ্যাক্সেলারেশন নিয়ে কথা বলি, ফোর্স নিয়ে কথা বলি, এবং একই সাথে আমি কোন টাইপের এনার্জিতে কনভার্ট হচ্ছে সেটাকেও একই সাথে আলাপ করি। কারণ এই জিনিসটাও আমাদের সিলেবাসের একটা ইম্পর্টেন্ট পার্ট, টু আন্ডারস্ট্যান্ড দ্য এনার্জি কনভার্সন ফর ডিফারেন্ট সেগমেন্ট অফ দ্যাট ভিটি গ্রাফ। সো একটা জিনিস হচ্ছে যে কোন একটা অবজেক্টকে, আমি একটা সিম্পল এক্সাম্পল বলি, আমি একটা সিম্পল এক্সাম্পল বলতেছি এখানে। এই ডিসকাশন গুলো আমাদের ওয়ার্কিং জীবন চ্যাপ্টার আবার আসতে পারে, বাট ফর দ্য টাইমিং আই এম গোনা ট্রাই টু ডিসক্রাইব দিস ইন মাই ওন কনভিনিয়েন্ট ওয়ে। Hi. So this is how I actually teach it. It goes on in a downright direction. Okay. So একটা জিনিস হচ্ছে যে ফার্স্ট অফ অল যে আইডিয়াটা আমি এন্টারটেইন করি সেটা হচ্ছে হোয়াট ডু ইউ মিন বাই দ্য ওয়ার্ড পটেনশিয়াল এনার্জি। পটেনশিয়াল এনার্জি এই জিনিসটা অ্যাকচুয়ালি কি মিন করে? পটেনশিয়াল এনার্জি বেসিক কনসেপ্টটা হচ্ছে whenever you change the certain variable of an object while you have to work against some pre-existing forces. I'll say it again. Whenever you change certain variable of an object, certain variable ki seta pore boltechi, certain variable of an object, so that you have to work certain pre-existing force against, you have to work certain, you have to work against certain pre-existing forces, you provide potential energy in the system. আমি এক্সাম্পল বলি, মনে করো খুবই সিম্পল এক্সাম্পল, ইলাস্টিক পটেনশিয়াল এনার্জি। মনে করো একটা স্প্রিং আছে এখানে, ঠিক আছে, মনে করো এটা একটা স্প্রিং, এটা হচ্ছে স্প্রিং এর ন্যাচারাল স্টেট, এটা হচ্ছে স্প্রিং এর ন্যাচারাল লেন্থ, আনএক্সটেন্ডেড লেন্থ। এখন আমি যদি স্প্রিংটাকে এক্সটেন্ড করতে চাই, আমাকে মনে করো একটা পাশে আমার ওয়ালে ফিক্স করা আছে, আমি এই পাশে মনে করো একটা সার্টেন ফোর্স অ্যাপ্লাই করলাম, ফোর্স অ্যাপ্লাই করে কিছুটা এক্সটেন্ড করলাম। আর স্প্রিং এর বিহেভিয়ার হচ্ছে যে যখনই আমরা একটা স্প্রিং কে ডিফর্ম করব, সেই ডিফর্মেশনের এগেইনস্টে একটা ফোর্স জেনারেট করবে, যেটাকে আমরা ইলাস্টিক ফোর্স বলি। And within the limit of proportionality, that force follows the Hooke's law, which is given by F equals to kx. এটা ইলাস্টিসিটি খুব বেসিক একটা ল, এটা আমরা দেখবো ইন ডিটেইলস পরে। But object will always try to maintain its original shape or size, however you say it. So solid objects has a natural tendency to maintain their original shape and size. So whenever we try to deform an object, the object naturally produces a resistive force from within itself, which we call the elastic force. So if we want to deform an object, we have to work against that force. মনে করো এই স্প্রিংটাকে এইদিকে আমি পুল করলাম, মনে করো হচ্ছে লেটস সে 5 সেন্টিমিটার পুল করলাম। 5 সেন্টিমিটার পুল করার পর দেখা গেল যে এটার এই ডিরেকশনের যে ফোর্স, সেটা মনে করো হয়ে গেছে হচ্ছে 2000 নিউটন। লেটস সে দিস স্প্রিং ইজ ভেরি স্ট্রং। এখন মনে করো আমি যে ফোর্স দিয়ে পুল করতেছিলাম, মনে করো সেই ফোর্সেরও ভ্যালু ছিল হচ্ছে 2000 নিউটন। তার মানে কি, আমি 2000 নিউটন যখন প্রথমে অ্যাপ্লাই করা শুরু করছি, তখন কোনো ফোর্স এখানে ছিল না। যখন আমি আমার এক্সটেনশনটা 0 থেকে আস্তে আস্তে 5 সেন্টিমিটার পর্যন্ত বড় করছি, as I increase my extension from 0 to 5 centimeters, slowly the pull of this force increase, because that's what the equation tells us. As x goes higher, so the elastic force will also go higher. F equals to kx. It's just a product, and k is a constant. So these two are the main variables which are involved to each other. So let's say this happened, that I was pulling by 2000 Newton force. Whenever the spring was extended by only 5 centimeter, the elastic force became 2000 Newton. At this point, I cannot pull this any further, which means to make this extension possible, by applying a 5000 Newton force, I made a displacement of 5 centimeter for the entire spring. So this amount of work that I have done by the application of force will be stored within the spring as energy, and that is a type of energy which we call potential energy. For this example, we'll call this elastic potential energy. This can be, there can be other scenarios as well. একটা common scenario বলি, সেটা হচ্ছে gravitational potential energy. Let's say we have the ground over here, an object is located over here, and it has a mass of m. The earth is pulling the object downwards by a force of mg. Now, if I want to lift the object, let's say from this position to this position, if I want to bring the object to this height, I have to apply a force onto this object in the upward direction that would be at least equal to mg. And then I can move the object to this position. And by moving this position, I would have to, let's say this is our value h. If I apply a force of f has to be at least equal to mg. Average value of f has to be equal to mg. And eventually, by applying this F force, I will have to move the object in this direction to this new position. So the amount of work that I have to done is given by the product of these two variables. So force multiplied by the distance, in this case height, gives you the work done, and that work done will be stored within the object as GP. So এখানে আমার অবজেক্টের মধ্যে যতটুকু potential energy ছিল, বা let's say if this is considered as h equals to 0, আমরা বলবো এই পজিশনে কোনো potential energy ছিল না। এই পজিশনে আমাদের অবজেক্টের মধ্যে কিছু potential energy, in this case which is called gravitational potential energy, because we are working against the gravitational force, which is the weight of the object. So এই পজিশনে আমাদের অবজেক্টের মধ্যে কিছু gravitational potential energy স্টোর হবে। ওই gravitational potential energy ভ্যালু হবে এক্স্যাক্টলি f এর সমান। এখন এই f টা হচ্ছে প্র্যাকটিক্যালি mg এর সমান। তার মানে হচ্ছে আমি যদি f টাকে mg দিয়ে রিপ্লেস করি, I'm going to get mgh, which means to lift the object from this level to this level, the amount of physical work that we have to do can be expressed as mgh, which is also the expression for gp, which is mgh. Why am I telling all these stuff? To give an idea about potential energy. The potential energy is the type of energy that we introduce within a system by working against a pre-existing force. So আমাদের কোন একটা সিস্টেমের existing force এর against যদি কাজ করি আমরা, তাহলে আমরা তার মধ্যে এনার্জি, potential energy স্টোর করব। Whereas সিস্টেম যদি তার available force কে ইউজ করে কাজ করে, তাহলে তার potential energy কমে যাবে। এটা মানে আবার কিরকম? এটা মানে হচ্ছে এরকম যে মনে করো একটা অবজেক্ট এই হাইটে আছে, আমি এই হাইট থেকে অবজেক্টটাকে রিলিজ করলাম, আর্থ টেনে তাকে নিচে নামায় ফেললো। যখন আর্থ টেনে তাকে নিচে নামাবে তখনই তার জিপিটা কমে যাবে। যত সে আর্থের কাছে আসবে, এইচটা যত কমতে থাকবে তত তার জিপিটা কমে যাবে, এবং ওই জিপিটা তখন অন্য টাইপ অফ এনার্জিতে কনভার্ট হতে থাকবে। Typically what happens that if we consider air resistance 0, if we consider air resistance to be 0, then a falling object's GP perfectly converts into kinetic energy. যত নিচে পড়বে জিপিটা আস্তে আস্তে কাইনেটিক এনার্জিতে কনভার্ট হয়ে যাচ্ছে। I should give an arrow over here. So GP converts into kinetic energy, and over the same amount of time, or falling through the equal amount of same amount of distance, the amount of GP change should be exactly equal to amount of K change, which means GP would be going down, K would be going up. যতটুকু GP খরচ হবে ততটুকু kinetic energy gain হবে, so that the total amount of energy will remain constant, which is also another law which we call the law of conservation of energy. এটা পরে আসতেছে, but potential GP gravitational potential energy কনসেপ্টটা বুঝা গেছে কিনা বলবান?
Yes, sir.
মানে যারা অ্যাটলিস্ট আগে কখনো পড়ো নাই, এই মানে গ্রাউন্ড জিনিসটা, মানে প্রাইমারি যতটুকু বললাম অতটুকু বুঝা গেছে কিনা কনসেপচুয়ালি? বুঝা গেছে। এটা হচ্ছে একটা জিনিস। আরেকটা জিনিস বলি আমি, সেটা হচ্ছে what do you understand by frictional loss? What do you understand by frictional loss or resistive loss? Frictional loss is basically how much work we have to do, or how much energy we have to spend in order to overcome the existing friction of a certain system. In order to overcome the existing friction of a certain system. Now, what would this mean? I mean, what do I mean by that existing friction? Let me give you a simple example. ফিকশন আমরা একটু কিছুক্ষণ পর ফিকশন আমরা এখনই ডিটেইলসে পড়তে পারি। ফিকশন একটা খুব ইন্টারেস্টিং এবং খুব ইম্পর্টেন্ট আইডিয়া। আচ্ছা, আমি এটা এই পার্টটুকু ডিটেইলসে বলতেছি, কারণ ফিকশন আমাদের এই চ্যাপ্টারের কনসেপ্টে আছে। ফিকশন আমি যদিও we use the idea of fiction a little bit earlier to explain the concept of Newton's third law, which I considered that it was understood because you said that it was okay. But then again, if you have any question further later down, you can always ask me in the class, or you can ask me in the messenger as well. For example, Ryan asked me a question which I responded to. Do you know question answer by so Ryan? যেটা আমি জিজ্ঞেস করছিলাম দেখছো?
Yes, sir.
So what you said is perfectly all right. Both of the expressions that you've used, both of them are okay. And we could either say that, but mathematically that would be becoming smaller, but we only talk about the magnitude because we've already mentioned that it is negative. Yeah.
Yes.
Okay. Beautiful. So for frictional loss, frictional concept একটু বলি। মনে করো এটা একটা surface. Let's say this is a surface, rough surface on which we have placed an object. At the contact region, we're gonna have some mesh of two bodies. And for physical objects are actually never perfectly smooth. If you go at atomic level description, objects always have nooks and crannies and unevenness. No matter how much polish you make them, nothing is absolutely smooth. I mean, a zero friction scenario is practically unimaginable. I mean, it's imaginable maybe, but it's unachievable in most cases. For most practical purposes, it's unachievable. So frictional basic idea হচ্ছে যে এই দুটো object, when if we try to, how do we define the term friction? Whenever two objects are in contact with each other and try to move, being in contact with each other, whenever two objects try to move while being in contact with each other, there exists a resistive force against that motion. এই কনসেপ্টটা খেয়াল করো, আমি আবার বলতেছি, whenever two objects try to move while being in contact with each other, there exists a force which works against that motion, or which works to resist that motion. This resistive force is what we call the frictional force, or this incident of this sudden resistance is what we call friction. তার মানে হচ্ছে যতক্ষণ পর্যন্ত এই অবজেক্টটা এই সারফেসের উপর চুপচাপ বসে আছে ততক্ষণ পর্যন্ত আমাদের এখানে কোনো রকম frictional force available হবে না. So as long as the object is stationary over here, there is no frictional force. The moment we're going to try to move this object in any direction while the two surfaces are in contact, we're not lifting it up. For this discussion, we're going to try to move it, let's say, towards right. So then the friction will start to work. And friction between two objects has a limiting value, or otherwise it has a maximum value. The value of friction between two objects cannot be infinitely large. So let's say you are trying to push this object with, let's say, acha ami kichu mathematical term dei. Let's say the mass of this object is 2 kg. Let's say whenever I'm pushing this object by 1 Newton, let's say this is my pushing force, and the frictional force will be labeled by, let's say, small f, and the resultant force will be given by this symbol. So আচ্ছা আমি এখানে কিছু ভ্যালু লিখি, মনে করো ভ্যালু লিখে তোমরা বুঝবে আমি কেন ভ্যালুগুলো লিখছি। Let's say this is my applied force, this is my frictional force, this will be my resultant force, which will be coming from the subtraction of applied force minus frictional force, which should be equals to ma, by the way. Resultant force equals to mass into acceleration, not applied force. Resultant force equals to mass into acceleration. এখন মনে করো এই অবজেক্টের উপর আমি যখন 1 নিউটন ফোর্স দিলাম, let's say both of these things would be given in Newton, Newton, and Newton. If I give 1 Newton force, let's say if the frictional force is also 1 Newton force, it means the object will have zero resultant force and cannot move, which means currently the frictional force is perfectly matching it. এই জিনিসটা ইম্পর্টেন্ট যে একটা অবজেক্টকে যতক্ষণ পর্যন্ত আমি অ্যাভেলেবল ফ্রিকশনের চাইতে ম্যাক্সিমাম ফ্রিকশনের কম ফোর্স দিব, সে এক্স্যাক্টলি অতটুকু ফ্রিকশনাল ফোর্সই প্রডিউস করবে। Let's say the maximum frictional force that it could possibly exist between these surfaces, let's say 20 Newton. তার মানে আমি যদি এখানে 50 নিউটন ফোর্স অ্যাপ্লাই করি, আমার ফ্রিকশনাল ফোর্স হবে 15 নিউটন। যদি আমি এখানে 15.5 নিউটন ফোর্স অ্যাপ্লাই করি, আমার ফ্রিকশনাল ফোর্স 15.5 নিউটনই হবে। Within this value, let's say this is the frictional force max, if max equals to 20 Newton. Within this value, frictional force and applied force will perfectly match each other, so the resultant force will always be zero. The moment we will apply a force that is slightly bigger than 20 Newton. Exactly 20 Newton করলে কি হবে সেটা আমি একটু পরে বলতেছি। What will happen if we apply exactly 20 Newton? I'm going to say it a bit later, but for that, I mean, let's say if we apply a force that is significantly bigger than the maximum frictional force of 20 Newton, let's say if we apply a force, so let's say 25 Newton, frictional force will take its limiting value, that is 20 Newton. And in that case, the resultant force will be 5 Newton, which would give us some acceleration, which can be calculated F equals to 2 into A, because I gave the mass of the object to be 2 kg. So এখান থেকে আমরা acceleration calculate করতে, acceleration will be 2.5 meter per second squared. 2.5 meter per second squared মানে হচ্ছে if we keep applying this force onto this object, every second its speed will increase by 2.5 meter per second. So at 0 second is 0. After 1 second, the speed is 2.5 meter per second. After 2 seconds, it will be 2.5 plus 2.5, which is 5 meter per second. After 3 seconds, it will be another 2.5 meter per second added, which means 5 meter per second plus 2.5 meter per second, which is 7.5 meter per second. So if you keep applying that force, it's very important. It's not that you're going to just push it once and then it's going to keep on accelerating forever. No, as long as you want the acceleration, you have to keep pushing the object by the same amount of force. So if you keep applying that force by the same amount of force every single second, you will have an increase of speed of 2.5 meter per second. That's the whole idea of acceleration. Now, what happens if we apply the exact 20 Newton force? What's going to happen if we apply exactly 20 Newton force? What happens then? Then the frictional force will also be exactly 20 Newton force. This is the scenario that we define to be critical equilibrium or limiting equilibrium. Critical equilibrium or limiting equilibrium. What this state essentially mean is that the object is on the verge of moving. It is about to move, but it is just not moving. So it's like that. It's like, let's say, a person who has no money, but no debt. So they are at zero money. This object is something like that. So they have opposing force that is perfectly equal to the forward force, which means they are at equilibrium, but they are about to move. Whenever we say that the object is about to move or it's a critical equilibrium, it means that currently the forces are producing a perfect equilibrium. So even if there is a small addition of force from any source, the object will definitely start to move, which means basically, let's say an ant comes in. Let me zoom in because I want to draw an ant. let's say at this condition, an ant comes in, and this is the ant with all of its, I should draw smaller, with all of its body, and here is the leg. And let's say with one of their hand, they are about to lean onto this surface. So they're about to take a lean on the object. This object can start to move by the application of this small force provided from this ant's leaning, not even pushing. That's what we mean by the word critical equilibrium, that the object has a perfect equilibrium, but it is about to move. A small addition of force is going to cause the object to move. এই আইডিয়াটা বুঝা গেছে ক্রিটিক্যাল ইকুইলিব্রিয়ামের কনসেপ্টটা?
Yes, sir.
এটা চেক করার কিছু উপায় আছে এক্সপেরিমেন্টালি, আমাদের পেপার 3 তে কিছু এক্সপেরিমেন্ট আছে যেখান দিয়ে যেগুলো ইউজ করে আমরা বিটুইন এ সার্টেন উডেন বক্স অর উডেন ম্যাস এবং হচ্ছে টেবিল সারফেসের মাঝখানে ফ্রিকশনাল ফোর্সকে মেজার করতে পারি। এই ধরনের কিছু এক্সপেরিমেন্ট আমাদের পেপার 3 তে আছে। সো তোমরা ল্যাব করলে সেগুলো পাবা, অথবা আমি হয়তো পরে কোনো সময় তোমাদেরকে আলাপ করতে পারি, ওইটা এখন লাগবে না। বাট এটা হচ্ছে ফ্রিকশনাল ফোর্স। সো হোয়াই এম আই টেলিং ইউ দিস? এটা বলার মেইন রিজন ছিল আমরা আলটিমেটলি ফ্রিকশনাল লস নিয়ে কথা বলবো। Frictional loss এর পুরো আইডিয়াটা হচ্ছে যে whenever there exists a certain friction, if we want to make some movement against some frictional force, we always have to keep on working to overcome that frictional force. এটা একটা এক্সাম্পল তোমাদেরকে বলি। মনে করো এই যে এখানে যে ভ্যালুগুলো আমরা নিয়েছি, let's say we are applying 25 Newton force on the object and the frictional force was 20 Newton, so the resultant force was only 5 Newton. এখন এই পরিমাণ ফোর্স অ্যাপ্লাই করে মনে করো একটা অবজেক্টকে আমি ওই অবজেক্টের উপর 25 নিউটন ফোর্স আমি অ্যাপ্লাই করলাম, 25 নিউটন ফোর্স অ্যাপ্লাই করে আমি মনে করো অবজেক্টটাকে 10 মিটার মুভ করলাম। লেটস সে আই মুভ দ্য অবজেক্ট বাই 10 মিটার। এন্ড কোশ্চেন হচ্ছে এই 10 মিটার মুভ করাতে আলটিমেটলি কি হবে? If I am providing that force of 25 Newton, the amount of chemical energy that I would have spent from my body, from within my body, the amount of work done, physical work that I have done by spending my chemical energy, that amount of energy would be 25 Newton multiplied by 10 meter, which is basically 250 joule. I have to spend 250 joule of chemical energy to convert that into physical work to push that thing by a distance of 10 meter. But the object had only a resultant force of 5 Newton. So the kinetic energy gain of the object would be equals to 5 into 10. কারণ অবজেক্ট কিন্তু অ্যাকচুয়ালি 25 নিউটনের টোটাল ইফেক্টে সে মুভ করে নাই। এই 25 নিউটন থেকে আউট অফ দিস 25 নিউটন, ফর এভরি ইনস্ট্যান্স অফ মুভমেন্ট 20 Newton was continuously spent to overcome the friction. The object could only experience an actual movement because of this 5 Newton. So the actual amount of work done, or I can say the kinetic energy gain of the object would be only 50 joule. So try to understand, this is the total work done by me, this is the actual work done by me, or this is the actual kinetic energy gained by the object. So what is actually happening? Within this process, 200 joule of energy is getting lost or is getting wasted. Why is this 200 joule of energy is getting wasted? This is the amount of energy that we call the frictional loss. So frictional loss is basically frictional force multiplied by distance, which is gonna be 20 Newton multiplied by 10 meter, which gives you 200 joule. It's the same formula, work done equals to force into distance. But whenever it is this force is constant, this force is the frictional force, this work done is basically work done against friction, which we call frictional loss. তার মানে হচ্ছে যখনই আমরা ফ্রিকশনের এগেইনস্টে কাজ করব, আমাদের ফ্রিকশনাল লস হিসেবে কিছু এনার্জি সিস্টেম থেকে বের হয়ে যাবে, যেটা আমাদের সিস্টেমে আর থাকবে না। সিস্টেমে থাকবে না বলতে আমি কি বোঝাচ্ছি? এই 25 নিউটন অ্যাপ্লাই করাতে আমার বডি থেকে খরচ হচ্ছে 250 জুল, বাট অবজেক্টের মধ্যে স্টোর হচ্ছে কত জুল? 50 জুল as kinetic energy. So বাকি 200 জুল তাহলে কই গেল? এই বাকি 200 জুল হিটিং ইফেক্ট হিসেবে আমাদের এই অবজেক্টের সারফেস অথবা এই অবজেক্টের কন্ট্যাক্ট অথবা অ্যাটমসফিয়ারের মধ্যে হিট এনার্জি হিসেবে স্টোর হবে, বাট কাইনেটিক এনার্জি হিসেবে থাকবে না। A certain fraction can be stored within this mass as heat energy. Certain part would be spread over this surface, and certain part would be heating up the atmosphere around the box and the object, but it will not be stored as kinetic energy. So that's the idea of frictional loss. Frictional loss is a concept of the amount of work that we have to do to continuously overcome the frictional forces. That's what we mean by frictional loss. এটা বুঝা গেছে?
Yes, sir.
আমি লাস্ট একটা জিনিসগুলো আজকে ক্লাস শেষ করে দিচ্ছি। লাস্ট একটা থিং, অল্প একটু সময় লাগবে। Because of this frictional loss, every car, no matter how well designed, no matter how latest, no matter how good, no matter how many horsepower, no matter how many cc of the engine, because of this frictional loss, every car has a top speed. Irrespective of how much torque it can produce, irrespective of how much engine power it has, no matter how big the machine is, every car has a top speed. Now, you might know why this is. If you don't, I would like to use this as a thinking exercise for the next class. So next class, we're going to talk about a little bit about the air resistance, which is a version of the frictional loss for the air. And after discussing about air resistance, we're going to go back into the VT graph for the parachutist. Thank you very much.
Sir, when will the next class be?
The next class is on the schedule is Wednesday 7 p.m.
Sir, by then will it not be Eid?
You need the routine?
No, sir, by then will it not be Eid?
বুঝি নাই বাবা।
Sir, Eid. Will it not be Eid?
ও আচ্ছা আচ্ছা, এর মধ্যে ঈদ চলে আসবে।
Yes, sir.
ঈদ কবে?